Hello everyone and welcome back to another Calc 2 video. In this video we're going to talk about how we can use partial fractions to help us integrate. So if you remember back to a pre-calc class you took somewhere along the line, we talked about partial fractions. And what that means is, let's say we have a function that looks like this. We're talking about rational functions, which means polynomial divided by polynomial. We're asking what fractions did we add together to get the sum? So partial fraction decomposition is undoing the addition that has happened. How do we figure out what were those two fractions? Well, we know that the least common denominator in this case would be x plus 1 times x plus 2. So one of the fractions had to have a denominator of x plus 1. The other fraction had to have a denominator of x plus 2. And then we just have to figure out, well, what would the numerators have to be? If we're talking about fractions that have to be proper fractions, that means that the degree of the numerator has to be less than the degree of the denominator. Then we could call these A and B, and we could set up a system of equations to help us integrate this. So we're going to have four cases that we're going to look at. We're going to look at non-repeating linear factors. That's what this one is. We have two factors that are non-repeated. So we're going to have two numbers that we're trying to find. We're going to have repeated linear factors that we're going to look at. We're going to have irreducible quadratics and then repeated irreducible quadratics. So let's take this problem and let's integrate it. So this problem in Calc 2 would start this way. It would say integrate x plus 2 over x plus 1 x plus 2 dx. Or maybe this is an even factor and we want to integrate. So we would start by using partial fractions and figure out what those fractions are going to be. If I can figure out what A and B are, then I would be integrating this thing, and that's going to be really easy to integrate. It's going to be an ln. So how would we find that system and set that up? Well, we're going to find the least common denominator. This fraction is going to be multiplied by x plus 2 over x plus 2. This fraction is going to be multiplied by x plus 1 over x plus 1. So when I do that, I'm going to have a times x plus 2 plus b times x plus 1 over that common denominator. And that's going to be equal to my original fraction that we have. Now, the only way that this side can be equal to this side is if this numerator is equal to this numerator. So x plus 2 has to equal, I'm going to go ahead and multiply this out, ax plus 2a plus bx plus b. So then we're going to compare coefficients. So I'm going to rewrite this so you can see what exactly I'm talking about. I'm going to group the x terms together and then group the numbers together. So you can see how these have an x in common. And then these are just numbers. And all this is equal to x plus 2. So if I compare coefficients, the only way that this term is equal to this term is if this coefficient is equal to this coefficient, which is a plus b. Likewise, the only way that this is equal to this is if 2 is equal to 2a plus b. And this is the number that's on the other side of these. This is a number. Okay, it does not have an x or anything with it. If I have two unknowns, I have to have two equations to solve it. And this is where I like to use matrices to help us solve it. Remember, we're going to have a column for A, a column for B, and then we're going to have the numbers that's on the other side. So the first equation says I have a 1a plus a 1b is equal to a 1. And then I have a 2a plus 1b is equal to 2. And then we're going to do RREF. We could do that in our calculator. I will show you how to do this on the Desmos matrix calculator. So here's the Desmos matrix calculator. And I won't show you this for everyone, but you'll be able to see it here. I had on my example 2 rows and 3 columns. So I need 2 rows and 3 columns here. And then we're going to type in the entries from the matrix. So 1, 1, 1. And then 2, 1, 2. I'm going to hit enter. So it's stored that matrix as A. And now we're going to do RREF of matrix A. And what that does is something called reduced row echelon form. It's going to solve the matrix for us. So in this case, we're going to get a 1 and we're going to get a 0 for that. So what this row is saying is that A is equal to 1 and B is equal to 0. So if we go back to our rewrite up here, if I integrate x plus 2 over x plus 1, x plus 2, that's the same thing as integrating 1 over x plus 1 plus 0 over x plus 2. So why did we get a 0 there? Well, you can see in the beginning, we actually could have reduced these to end up with just 1 over x plus 1. But that came out in the wash there when we did integration by parts. So we really just need to integrate 1 over x plus 1. And that's going to be a u substitution and giving us the ln of x plus 1 plus c. Let's do another one. Let's say we want to integrate x plus 2 over x squared minus 1. So our first step is to factor the bottom. That's the difference of squares. It factors in the x plus 1, x minus 1. Okay, nothing's going to reduce here. So we got to figure out how are we going to rewrite that. This is where we're going to do partial fractions. I'm going to do it down here. X plus 1, x minus 1. So it's going to be a over x plus 1 plus b over x minus 1. So this fraction would be multiplied by x minus 1. This fraction would be multiplied by x plus 1. And for that to be equal to that, then we have to compare numerators. So I'm doing a couple steps in one here. So I've got to compare coefficients in front of x, and then I've got to compare the numbers. So my coefficient in front of x here is 1. So I'm going to have 1 equals a plus b. And then I'm going to have the number 2 has to be equal to negative a plus b. So here's my system. Remember, we write this as coefficients of a, coefficients of b, and then numbers that's on the other side. So the second one is going to be negative 1, 1, and then 2. And then we're going to do RREF. Now you can solve using substitution or elimination. I like using matrices. And I'm going to solve the rest of these off screen. This is giving me 1001, and then I'm going to get negative 1/2 for A and 3/2 for B. So I could rewrite this guy as negative 1/2 over x plus 1 plus 3/2 over x minus 1. And then now I'm in a place where I can solve this. So let me continue down here. I would think about integrating these separately. Oops. What I don't gave you the answer there. Let's rewrite first. 1 over x minus 1 dx. Both of these are going to be ln. U is x plus 1, du is 1 dx. So this is in the form du over u, which integrates to x ln of x plus 1. Same kind of thing here. U is x minus 1, du is 1 dx. This integrates to ln of absolute value x minus 1. So there's our final answer for that. This is where you may want to pause the video, take a minute, and try this one on your own. So I would start by factoring that denominator. This is going to factor into x minus 6 times x plus 1. So let's write out our partial fractions. It's going to be equal to a over x minus 6 plus b over x plus 1. Our common denominator would be x minus 6 times x plus 1. So that first fraction needs an x plus 1 multiplied in. The second fraction needs an x minus 6. For this guy to be equal to this guy, the numerators are going to have to be equal once I find that common denominator on the right. So we're going to look at x's. We're going to look at numbers. So my coefficient over here for x is 1. That's going to be equal to a plus b. My number on the left is negative 3. That's going to be equal to a minus 6b. So there's my system. Let's plug everything into my matrix. Let's solve. I'm going to do that off screen. And this one has some fractions in it. So I'm going to have the calculator turn that into fractions, not that decimal that never ends. So A is 3 over 7 and B is 4 over 7. So what we really want to integrate right here would be 3 over 7 over x minus 6 plus 4 over 7 over x plus 1. So this is going to be ln. Both of those pieces are ln. I'm going to have 3/7 ln of absolute value x minus 6 plus 4/7 times ln of absolute value x plus 1, and then we're going to have plus c. So all of these cases are non-repeated linear. So let's do a repeated linear. Let's say we have 32 minus 5x over x cubed minus 8x squared plus 16x. So we need to factor that denominator. We could factor an x out, leaving us with x squared minus 8x plus 16. and that factors into x minus 4 times x minus 4. So you can see how we have that repeated linear there. So this guy is really 32 minus 5x all over x times x minus 4 quantity squared. So let's set up our partial fractions. So we're going to have a over x plus b over x minus 4 plus c over x minus 4 quantity squared. So you can see how we're setting this up. X is the first linear term. That one's not repeated. This one's repeated. Now, we don't know if we will need this guy and this guy. If we don't need this one, it will come out in the wash because the b would be 0. But we got to think about what would we have to add together? What are all the different possibilities that could get us to this? And then we're going to think about that common denominator, and it's always the least common denominator, which is what we have as a denominator on the left-hand side. So what is this guy missing? Well, that first term is missing an x minus 4 quantity squared. If I multiply this by x minus 4 quantity squared, I'll get that denominator. That second term is missing the x, but it's also missing one of the x minus 4s. And then that last one is missing just the x. So I'm going to multiply this out a little bit. This is going to be x squared minus 8x plus 16. This is b times x squared minus 4x. And this is c times x. That's got to be equal to 32 minus 5x. So notice this time we're going to have coefficients of x squared. We're going to have coefficients of x, and then we're going to have numbers. And if you need to multiply everything out and group like we did in the first example, that's fine. You can do that. On the left-hand side, we do not have an x squared, so its coefficient is 0. On the right-hand side, if I were thinking about multiplying this through, I would have an a as the coefficient of x squared, and I would have a plus b as a coefficient of x squared. Coefficients on the left of x, we're going to have a negative 5 on the right. If we were going to multiply through, we're going to have a minus 8a, a minus 4b, and then a plus c coming here from here. And then numbers. On the left-hand side, we have a 32. We multiply through here, excuse me, that's going to give us a 16 times a. And notice we do not have any other numbers. So we could plug this into a matrix, or we could just use substitution. We know right off the bat, let me do this in a different color. We know right off the bat that a has to be equal to 2. We divide both sides by 16, which means that I know what b is, because I know 0 equals 2 plus b. So negative 2 is equal to b. And if I know that, then I can find c. So negative 5 equals negative 8 times 2 minus 4 times negative 2 plus c. So that's negative 16 plus 8 plus c. It's negative 8 plus c. So it looks like 3 is going to be equal to c. So there's my a, b, and c. So what I really need to integrate is a, which is 2 over x, plus b, which is negative 2 over x minus 4, plus c, which is 3 over x minus 4 quantity squared. So that's what this problem has turned into. So I'm going to think about rewriting this and integrating each piece separately. And if you don't need to do that step, that's perfectly fine. Now those first two pieces are going to be LNs. The question is, what are we going to do with this guy? This is going to be a u substitution. Could rewrite that as x minus 4 to the negative 2. So if you're thinking about u sub, u would be equal to x minus 4. du is 1 dx. So then when we rewrite this, we're really integrating u to the negative 2, which equals u to the negative 1 over negative 1, or negative 1 over u plus c. So we're going to have 3 times negative 1 over our u plus c. Clean that up just a little bit. And there's one of my answers. If we wanted to, we could combine some things. This is really an exponent on this, so this is really an x squared, which means I no longer need the absolute value because it's always positive. Same thing here, that 2 is really an exponent. I no longer need the absolute value. And then I could combine these using log properties. So I could have x squared over x minus 4 quantity squared to simplify that. So any of these answers. Let's look at another one. We have 12x squared plus 8x minus 3 all over x cubed plus x squared dx. So notice every one of these, they were in proper form. The degree of the top is less than the degree of the bottom. I'm going to factor the bottom. I can factor out an x squared, leaving an x plus 1. So this is a repeated linear case. That x squared is really x times x, which is a linear term times a linear term. So we can think about this fraction, 12x squared plus 8x minus 3 over x squared times x plus 1, as a over x plus b over x squared plus c over x plus 1. Here's my setup for my repeated linear. So now we need to create that system of equations. This term, think about what it's missing. It's missing an x, and it's missing an x plus 1. That middle, to get that least common denominator, is missing the x plus 1. And then that last term is missing the x squared. So I'm going to rewrite this. If you need to FOIL everything out so you can see the system, that's perfectly fine. So I have x squareds, x's, and numbers. On the left, x squared is 12. On the right, that's got to be equal to, oops, I don't know why that's moving, equal to a plus c. On the left, I have an 8 in front of the x. On the right, if we were to multiply through, I would have an a plus b. On the left, I have a negative 3 as just the number. On the right, I would have just b as the number. So right off the bat, I know b is negative 3. So I can use substitution again instead of REF. You could do either one. Either one would be fine. So this would be a plus a negative 3. So if I add 3 to both sides, I'm going to get a equals 11. And then 12 equals 11 plus c. So it looks like 1's going to be equal to c. So then what I really need to integrate would be when I plug A, B, and C into this broken down piece. So 11 over x minus 3 over x squared plus 1 over x plus 1. So I'm thinking about integrating each piece separately. That second piece we would rewrite as x to the negative 2. So I'm going to get 11 ln absolute value of x minus 3 x to the negative 1 over negative 1 plus ln absolute value x plus 1 plus c. And now I'm going to clean this up just a little bit. So this is going to be the ln 11 ln absolute value of x plus 3 over x plus ln absolute value x plus 1 and then plus c. We could leave it like that, or we could rewrite it. This is really x to the 11th power. And I'm going to rewrite, reordering those last couple of terms there. And then I could combine those if I wanted to as x to the 11th times x plus 1. Notice that absolute value is still necessary in this case. Either one of these would be an acceptable answer. So that's the first two cases. Now let's look at case 3, which is an irreducible quadratic. What that means is it's not factoring over the real numbers. So let's say we want to integrate x squared minus 56 over x to the 4th plus 5x squared minus 36. Okay, well, this denominator is going to factor into x squared minus 4 times x squared plus 9. Okay, notice that's going to give me this back, and that first factor is actually a difference of squares. So when I rewrite this, I'm going to have denominators of x plus 2. I'm going to have a denominator of x minus 2. And then I'm going to have a denominator of x squared plus 9. Now, over a linear term, if we want it to be in proper form, where the degree of the top is less than the degree of the bottom, you have to have just a number. Same thing here. Okay, these are my linear terms. This is my irreducible quadratic. It does not factor over the real numbers. For this to be in proper form, I would have a linear possibly up here. So I'm going to call this cx plus d, okay, because this is a degree of 1 and the bottom is a degree of 2. If I don't need the c or the d, it will come out in the wash. We'll end up with a 0. We'll just have to see what we need in this case. So just like before, we're comparing this side to this side, but we need a common denominator over here, and it always has to be that least common denominator. I'm going to rewrite this as that factored form. So x plus 2, x minus 2, x squared plus 9. So I'm going to have x squared minus 56 equals, this fraction needs to be multiplied by x minus 2 and an x squared plus 9. This fraction needs to be multiplied by an x plus 2 and an x squared plus 9. That would give me the same denominator as here. And then this cx plus d has to be multiplied by that x plus 2 times x minus 2. And then we're just going to multiply stuff out. So this is going to be x cubed minus 2x squared plus 9x minus 18. This is going to be x cubed plus 2 x squared plus 9x plus 18. And this is going to be c times x plus d times x squared minus 4, which we're going to have to multiply out. So we're going to get cx cubed plus dx squared minus 4cx minus 4d. Remember, that's going to be equal to x squared minus 56. Now, that's the same thing as saying x squared plus 0x minus 56. Oh, I forgot the x cubed. We don't have an x cubed either, so it's 0x cubed plus x squared plus 0x minus 56. So you can see how we're comparing those coefficients on the left and on the right. So I need coefficients for x cubed, x squared, x, and then just the number on the end. So I have a 0x cubed, that's going to be equal to a plus b plus c. X squared, I have one of those on the left, that's going to be equal to negative 2a plus 2b plus d. X's, I got 0 on the left. I'm going to have a 9a plus 9b coming from here minus 4c. And then the number, I have a negative 56. That's going to be equal to negative 18a plus 18b minus 4d. This one's not going to be easy to solve by hand, so I'm going to create that matrix. So that first line is going to be 1a, 1b, 1c, no d's, and then the number on the other side is 0. This is going to be negative 2a, 2b, no c's, 1d, and that's equal to 1. That next one is going to be 9, 9, negative 4, 0, 0. The last one is negative 18, 18, 0, negative 4, negative 56. So when we do RREF, we're going to get 1, 0, 0, 0, 1, 0, 1, 0, 0, negative 1, 0, 0, 1, 0, 0, and 0, 0, 0, 1, 5. Just so you know, this is called the identity for a 4x4. So you may see me write it this way, identity for a 4x4 with that. So what this would mean is A is equal to 1, B is equal to negative 1, C is equal to 0, and D is equal to 5. So if I plug that in here, then what I'm really integrating is 1 over x plus 2 plus negative 1 over x minus 2 plus 0x plus 5 over x squared plus 9. Just making sure I plugged everything in correctly. And then we're going to think about integrating each of these pieces separately. So these two will be ln's. This is going to be an arctan. So we're going to get the ln of the absolute value of x plus 2 minus the ln of the absolute value of x minus 2 plus 5. And arctan is 1 over a. Arctan of u over a And then we're going to have a plus c. I'm going to clean this up just a little bit. We could put those LNs together. So we could say this is the ln of x plus 2 over x minus 2 plus 5 over 3 arctan of x over 3 plus c. Either answer would be fine. And let's do one where we have a repeated irreducible quadratic. Let's say we want to integrate 5x to the 4th plus 32x squared plus 48 all over x times x squared plus 4. So we see we have a linear term, and then we have a quadratic term, and then we have the quadratic repeated. So our setup's going to be really similar to when we have that repeated linear term. We're still going to think about the fact we could have a linear up here and here. So let me just draw an arrow here. And then I'm going to rewrite. So this called the guy. Is equal to this. For that to be true, the numerators have to be the same when we have that common denominator. Oops, I'm missing the squared there. We can go back and fix that. That should be x squared plus 4 quantity squared. Must not have caught that when I wrote it earlier. So there's my setup. So that first fraction is missing the x squared plus 4 quantity squared. This fraction is missing an x and an x squared plus 4. And then this fraction is missing just that x there. So if I FOIL this out, I'm going to get x to the 4th plus 8x squared plus 16. And this is going to be bx plus c times x cubed plus 4x. And this is going to be dx squared plus ex. I think I'm going to need a little bit more space. I'll multiply this out. So this is bx to the 4th plus cx cubed plus 4bx squared plus 4cx plus dx squared plus ex. Supposed to be equal to 5x to the 4th plus 32x squared plus 48. So you can see how we've got 5 different variables. We've got things in front of an x to the 4th. We're going to have things in front of x cubed and x squared and x, and then just a number that's on the other side of the equals. Or just a number. So we're going to have a 5 that's equal to a plus b x cubed. We do not have one on the left. I'm going to have a c here. So right off the bat, we know C is 0. X squared. I have a 32 on the left. That's going to be equal to 8a plus 4b plus d. X's, I don't have one on the left. That's going to be equal to 4c plus e. And we know something, right? If we know c is 0, then we know e is 0 also. And then numbers, we have 48 on the left. That's going to be equal to 16a. If I divide both sides by 16, I'll get a. So a is equal to 3. And we got enough information to solve this without using a matrix. If you're not sure, you could always use a matrix and plug everything in. So 5 equals 3 plus b. So 2 is equal to b. And then, let me actually take this down here. 32 equals 8 times a plus 4 times b plus d. So 32 equals 24 plus 8. So D is 0. So we're going to plug everything we know back in here, and that's what we're actually integrating. So A is 3, B was 2, C was 0, D was 0, and E was 0. So what that tells us is that this guy could actually reduce by a factor of x squared plus 4 if we were to factor that numerator. So this is going to be 3 over x plus 2x over x squared plus 4. And this is going to be 3 ln absolute value of x. This is already in the form of du over u, so it's going to be plus ln of x squared plus 4 plus c. And the absolute value is really not necessary here because that guy's always going to be positive. So we could write that this way. If we wanted to combine these, we could move this guy back. And we could use log properties to get that as a final answer. Either answer would be fine. So where do I use partial fractions? If I have a rational function that's in proper form, and I need to break it down into the original fractions, that's where I use partial fractions. If it's not in proper form, so the top degree is bigger than the bottom degree, then your first step would be using long division, and then you can apply partial fractions.